Hey guys, this is Menu from IICAE. Okay, we provide tutorials to CAD, CA, CFD, MBD, and this is a contact number you can contact for the further classes. We are Altair Hypermesh Authorized Professional Training Center, and today's topic will be plate deflection analysis. First, we will go through the basic representation what it is about. So, basically, we do have a wall, we have a plate, and the plate is fixed to wall at a certain point. We apply certain load because of mass at the end, and obviously there will be a displacement because of the load. The displacement can be categorized as the deflection in the plate, and it can be given with the formula FL cube upon 3EI, where F is the force, L is the length of plate, E is the elastic modulus of steel, the material for the plate, and I is the moment of inertia that depends on the shape of the plate. For here it will be rectangular. So first of all, start with the problem definition. The mass according to our units will be 0.001 ton. The weight of the plate is 10 mm, the height of the plate is 5 mm, and the length is around 10 mm. The elastic modulus of the steel is 2.1 10 raised to the power 5 megapascals. We need to find the displacement in the steel and the stress generated in the plate. Okay, so first we check the analytical solutions. This is the steel plate with the 100 mm length and a 5 mm height with a 20 mm width. Now coming to the solutions, first we'll calculate the force. That force is equal to mass into acceleration due to gravity. The mass provided was 0.01 ton and acceleration due to gravity is 9810 millimeter per second square. So basically that comes to be 98.10 ton millimeter per second square. The moment of inertia here, the shape of plate was rectangular. So the moment of inertia of rectangular is base into height cube divided by 12, that is 10 millimeter into 5 millimeter cube, 5 millimeter cube divided by 12, that turns out to be 104.16 millimeter squared. Now for the deflection, the formula was FL cube upon 3EI, where F is force, L is length of the plate, and E is the elastic modulus of steel, and I is the moment of inertia of the shape. So now doing the calculations, we get 1.48 mm as a deflection of the steel. Now this was the analytical calculations. So okay, as whatever we did there, that was analytical calculations for the deflection of plate. So we are gonna do a numerical analysis for the deflection of plate with Hypermesh as a preprocessor, Optistruct as a solver, and Hyperview as a postprocessor. The basic work of the preprocessor is to generate and create the model. The solver is just to solve the calculations, and the Hyperview just uh, just uses that calculations results and give a graphical representation of that. So first it was a place deflection, so we need to create a plate deflection model. First we'll go to Hypermesh, then we'll go to Optistruct panel, and we'll start with the first creation of the geometry. Okay, first we'll go to nodes. As we know that the basic length of the plate was 100 mm and the width of the plate was 10 mm. The thickness was around 5 mm. So first we'll understand that the hypermesh is a coordinate system. So we need to provide coordinates for the end extreme corners of the plate. We'll go to nodes. We'll create a node in origin. Let's say create. Now it's not visible here. We need to press F for fit to screen to get that node visible. Once we press F, it is visible now. Okay. Now we need to put the Y as 10, as we know that the thickness is around 10 mm. So we can press the F again to fit to clearly show those two nodes. Now the other two nodes will be in the extreme end, that is the length of the plate, that's 100 mm. Now we'll see there, that's one created and one at the original part, so it will be okay. So we have the four extreme corners. Okay, now we'll go to surface and we'll go to this splines option. we'll select the node counter and we'll select the node list 1, 2, 3 and 4. Now we'll press create and we can see a bond surface is being created. Okay, we can remove the temporary nodes by going to temporary nodes and clear all. So basically this is the surface for the this is the plate surface. Okay, now what we need we as we know that component is being created as auto, we can rename it as like we can rename the component, let's say rename into plate. And now we know, as we know that it's a finite element process, so we need what it is, we need to do the discretization of the whole surface into smaller elements, and that can be done by meshing it. So we will go to 2D auto mesh, we'll select the optimum mesh size as 5 and we'll select the surface. Once the surface is selected, it will be highlighted as white. Or now once we create a mesh, we can see that the mesh is being created. Now we'll press return to save the meshing. Okay, now from here we can hide this surface, and from the this mesh counter we can switch to the shaded mesh elements. Okay, now the representation is quite clear. Now we need to create the steel property, steel data, material data, that is being steel. So we will go to the material data, we'll click on material, let's say name steel. Okay, steel is an isotropic element, so isotropic type, and we'll have card images mat1 and mat4 and mat-tf. So mat1 is basically for elastic elastic structural, mat4 is being used for thermal. So we'll select mat1 as an elastic material. Now we'll click on create edit. We need to provide the information, basic information, properties of the material like elastic modulus, the Poisson's ratio, or the density. So this is being predefined by the system software as E. Once we create or active them, like Poisson's ratio is 0.3, E as mentioned is 2.1, 10 raised to the 5 megapascals, and rho is 7.9, 10 raised to the minus 9. Once we'll press return and we can see that the material is being created. Now we'll create the properties. So we'll select the property counter and we'll let it say that 2D property 2, because these are 2D elements. Now we can see the type is 2D. Now we'll create a card image as P shell, and material that is being created as steel. We'll go for create edit and we can see T will define my thickness that according to the question was 5 mm. Okay, now once the thickness is being decided, we can create return. Now we'll go to component and we'll press update, so the created components can be shifted to the model. Okay, now we'll click on the component. So card image will be no card image property will be defined as the created property of 2D. So 2D property being created, the steel is automatic, material is automatically selected, we'll get update and now we'll press return. Okay, to check the detailed representation, we can go to here and we can 2D detailed element representation that will show the thicknesses being created. Okay, now we'll switch back to it. Now what I need to do is create the loads according to the question. So first of all, to creating loads we need to know the what were the conditions, and the conditions were it was fixed to a wall on the one side and it was provided with the load on the another side. Okay, so first select the loads on the first create a fix it to a wall. For that we need to go to load collector, we'll name that spc is single point constraint, and we will select the card image as no card images and we will create. Okay, we can see here that the spc is the active load collector. So whatever load is being created, it can be shifted to the active load collector. Load collector basically stores the data of the load provided. Okay, and we'll go to analysis, we'll go to constraints. Okay, we'll select these nodes, and once we select these nodes we can see that these are degree of freedoms that needed to be restricted. Basically spc restricts the movement in the selected degree of freedom. If we unselect the provided degree of freedoms, then it will allow the movement in that area. Now as we can see that the all of these are selected, so we can directly create and will restrict completely restrict the movement. We can see the triangles are basically the geometrical representation for the SPCs. And now these SPCs are being created. Okay, now can return, and we need to create a load collector for the force. We'll go to load collector, we'll type force, and then we can again click on create. We, as we send the current load collector is force. Now we'll return it. Now I need to know that these three nodes are will be my position for my force. Okay, we'll go to forces, we'll select the nodes, and we'll give the direction. My direction can be selected as like, once we, it will be on a negative z axis, so I will select the direction as z axis, and we'll provide a magnitude that if we divide the force that was 98.10 into three nodes, then each node will be having 32.7 Newton according to it. Now if the load is being created, it should be negative because it's a minus z axis. We'll create on, click on create, and we will see that a force is being created. Okay, now we need to create a load collector. That load collector will define the relation between the SPC and the forces. So therefore that we need to go to analysis, we'll go to load steps. Load step, we'll say that it is deflection, and we'll create SPC and click on load, and we'll go to SPC as SPC and load as force. Now it is a linear static simulation. We'll create basically what are load step. Load step creates a relation between the provided load collectors, and it defines the type of the simulation that needed to be done. Okay, now the model is ready, and now what I need to do is I need to go to analysis. I need to select on Optistruct. I'll save it in, let's say, on documents. We'll create a folder for plate deflection plate. Let's name it plate. It is open. HM can be written as HM1, and now save it. We'll select that analysis as all, and we'll do Optistruct. Once we press on the Optistruct, the Optistruct dialog box will soon appear. That will be solver view for the Optistruct. We can see the progress here, and as it is 100%, and when the analysis completed message appears with no errors, we can directly we know that the analysis is complete. As the analysis ended, and we got a message about analysis completed in the Optistruct solver dialog box. That means no error were found, and we will click on the result. The Hyperview pop-out will open, and now we can see the results in the Hyperview. Basically, it's a post-processor that shows the calculated results. There's a graphical representation of the calculated results, visual representation. For the visual representations, we'll go to contour. Contour, we have options in the result type as displacement for or element displaces. Then we'll go for the displacement and go for the magnitude, and we'll select on apply. While applying, we can see the red region, blue regions, and we'll see the contour plot. So 1.48 is the maximum displacement in the red region, and according to the analytical calculations, we also figured out that 1.48 mm is the displacement in the plate deflection analysis. So we can see that the numerical analysis and the analytical analysis are verified right now. And for calculations of the stresses, we will go to result type element stresses, and we'll click on the apply. We can also see that the stresses contour is being made for the von Mises stresses with maximum stresses in this the area where it was fixed to the wall. And for the visual animation, we can go to and click the play button, and we can see the play animation of the later how it will be acting according to the load. And now this is the correlation between the analytical and the numerical analysis of the plate deflection analysis, and we can see the values are being quite equal to each other.